Hello everyone, welcome to this lecture. In the previous lecture we studied frequency domain representation of discrete periodic signal. In this lecture we are going to study frequency domain representation of discrete aperiodic signals which will lead us to the concept of discrete time Fourier transform, that is DTFT. Then we will look at the relationship between the DFS and DTFT. Then we will define discrete Fourier transform, that is DFT. And then we will see that which Fourier transform or which tool, that is DFS, DTFT or DFT, should be used in practice. Then we will look at single sided spectrum, and then the relationship between the time domain parameters and frequency domain parameters of discrete signal and DFT. And at the end we will briefly look at what is fast Fourier transform, that is FFT. So therefore today we are going to talk about frequency domain representation of discrete aperiodic signals. So if the continuous signal is aperiodic, right, then the corresponding discrete representation of the signal would also be aperiodic. And let us represent this discrete aperiodic signal by say x a n. Okay. So the suffix x is suffix a is used to represent the aperiodic nature of the signal. So the strategy we are going to use to find a Fourier representation of this signal is similar to the one we adopted in finding the Fourier transform of an aperiodic continuous signal. Okay. And so therefore what we do here is, first of all we define a corresponding discrete periodic signal, right, which will represent by x n, and this is obtained by periodically repeating the copies of signal x a n. Okay. So if we show it by figure, so we have, let us consider a pulse signal. So this is nothing but the signal x a t, that is the continuous signal, and let us say this signal is like a rectangular pulse signal. And now the corresponding discrete signal is this we are going to call as x a n, and this signal is basically let us say we have sampled it, and let us say there are 3 samples representing this pulse like this. So this is the corresponding discrete signal, which is now the aperiodic signal, and we are interested to find the frequency domain representation of this signal. And what we do now is that we construct a corresponding periodic signal x n by repeating the copies of this aperiodic discrete signal after every time t, right. So this is, we are repeating it like this in both directions, right, and such that this time period is t, right, and depending upon the sampling rate, this time period t will contain n samples. So if fs is the sampling frequency, then the n number of samples in this capital T time period will be n. And now what we say is that if we increase this time period t gradually and make it tending to infinity, then what is going to happen? The number of samples also would tend to infinity, right, because sampling frequency is same, and then in the limit this x n, the discrete periodic signal, will become the discrete aperiodic signal x a n. And therefore we can say that x a n is nothing but limit of x n when n tends to infinity. So this is how we can define the aperiodic signal as limit of the discrete periodic signal when the time period of the signal tends to infinity. And now what we are going to do, for xn we know the discrete Fourier series, which is the frequency domain representation of xn, and by taking the limit of that DFS we hope to obtain the Fourier representation of the discrete aperiodic signal. So let us do that on the next page. So we write down now the DFS of xn, and this already we have studied in the previous lecture. The DFS of xn is given by xk is equal to 1 by n xn e to the power minus I k 2 pi by capital N into small n, right, with n varying from 0 to n minus 1. So this is the discrete Fourier series of the signal xn. Now here 2 pi by n we call as the fundamental frequency, and we represent it by uppercase omega naught, right. So this is nothing but the fundamental frequency of the discrete sequence. And the unit of this, you can note here, it is basically radians. The unit of this is radians. So this omega naught, uppercase omega naught, is related to the frequency in radian per second by this relationship. Okay. So here omega naught is the fundamental frequency in radians per second, and they are related, the uppercase omega naught and lowercase omega naught, they are related by this relationship. So therefore we can now write down xk as 1 upon n, n is equal to 0 to n minus 1, x n e to the power minus k uppercase omega naught n. Okay. And now if we want to take the limit when the number of samples n tends to infinity, then we should see that how these variables undergo change. So we see that the discrete frequency component, discrete frequency, which is k omega naught, right. So k omega naught is the frequency of the kth component, and when n tends to infinity, this omega naught is going to become infinitesimally small, and therefore k into omega naught will become a continuous variable. Okay. No longer the frequency components are discrete, they become so closely packed that the frequency becomes a continuous variable, and therefore this k omega naught we should be representing by a continuous variable omega. Okay. The limits in the summation also would basically change from n is equal to 0 to n minus 1 to now, because samples have become infinity, the in both directions this limit would change from n is equal to minus infinity to plus infinity. In addition, the strength of individual frequency component xk, that will also no longer be finite, it will become infinitesimally small, right, because the components have become, the frequency component have become continuous, they are no longer discrete, right. So the strength of individual specific frequency components becomes very small, infinitesimally small, and hence instead of finding the limit of xk, we find the limit of xk upon 1 by n. So let us incorporate these changes here. So let us take the limits, limit of when n tends to infinity, then now we want to find the limit of xk upon 1 by n, right, and this is equal to n varying from and this is equal to limit n tending to infinity, okay, and summation n is equal to 0 to n minus 1 x n into e to the power minus I k omega naught n. So now let us take the limit. So on the right hand side, let us incorporate the modifications just now we discussed. and those modifications would be, now the summations would proceed from minus infinity to plus infinity, right. And now the signal xn, when n tends to infinity, signal xn becomes the original aperiodic signal, right, and that we can write as x a n into e to the power minus I. Now k omega naught will become omega n. So we see that this right hand side now has become a continuous function of frequency omega, okay, and therefore the left hand side we can symbolically represent it as a some function which depends on continuous variable omega. So let us represent this by x, and this is nothing but x a, and this is omega. So here therefore this is the expression we get, right. So here x a omega represents the frequency domain representation, right, of discrete aperiodic signal, right. And since it is the nothing but the Fourier transform of the discrete periodic signal, which is a discrete time signal, this is also referred as discrete time Fourier transform, okay. So this is also referred as discrete time Fourier transform, right, and it is abbreviated as DTFT, okay. So now we can make some observations about the nature of x a omega, right. Let us go to next page. So let us look at the nature of x a omega. The first observation is that the frequency omega is continuous, right. So x a omega, the spectrum is continuous, which means that its value is defined for every frequency omega. So it is a continuous spectrum. So it is a continuous spectrum. Another observation is that if you look at x a omega plus 2 pi r, where r is an integer, right. So if you increase the frequency by amount 2 pi r, that is with r as an integer, then this is nothing but x a omega itself, right, because the unit of omega, the uppercase omega, is radian, and if you increase this radian by 2 pi radian, there should not be any change in the value of x a, right, and therefore we see that x a is now periodic. So x a is periodic, and periodicity is 2 pi. So after every 2 pi radian on the frequency axis, the spectrum is going to repeat. Now we can also obtain the spectrum in terms of the radian per second, right. That is, if the frequency axis has to be in radian per second, then we can obtain this by simply dividing this by delta t. So by dividing x a uppercase omega by delta t, we get the spectrum in terms of the radian per second, just a scaling factor. So let us know for the pulse signal, right, that aperiodic discrete pulse signal, let us try to sketch what kind of the DTFT or the Fourier transform is going to look like, right. So let us do that. So this is, here we are going to now plot x a omega, and on this axis you will have omega frequency, and now we are going to plot. So you can see this is going to be periodic, x a omega is also going to be periodic, and what will be the periodicity? The periodicity will be the 2 pi upon delta t, because 2 pi is the periodicity of x a uppercase omega, and therefore periodicity of xa lowercase omega would be 2 pi by t, and 2 pi by t is nothing but 1 upon t is nothing but sampling frequency, and therefore this becomes the sampling frequency in radians per second. So it means the periodicity of xa omega in radian per second is nothing but omega s. So after every omega s frequency range, the DTFT is going to repeat. So therefore let us mark that first. So let us say this is 0, and then we have let us say this is Fs, and then we have this is 2Fs, and on this side we have this minus Fs, and then we have minus 2Fs, and so on, right. And so now how the spectrum is going to look like? So we will have the spectrum like this, and then we have something like this, right. And similarly here also we have and so on, right. So what we see that the this part of the spectrum from 0 to Fs, it repeats, right, and we can also say that if this is minus Fs by 2 and this is say plus Fs by 2, so we can also look upon minus Fs by 2 to plus Fs by 2 as the basically the spectrum which is repeating on either side, okay. So now in this way you can see we have found a Fourier transform of the discrete periodic signal, that is which has led us to basically the concept of DTFT, and we obtained it as the limit of the DFS of the corresponding discrete periodic signal. So the question arises that is there a relationship between the DFS and the DTFT we got, okay. So the relationship between DTFT and DFS, okay. So it can be shown that the DFS, that is xk, okay, it is a sampled and scaled version of the DTFT. This is based on the result that xk turns out to be equal to 1 by n x a k omega naught, okay. So therefore if we take the samples of xa at k omega frequency, discrete frequencies where k is varying from 0 to n minus 1, then all those samples taken from xa and scaled by factor 1 by n effectively give us the discrete Fourier series for one period of the signal, okay, the one period of the discrete Fourier series. So this is an important result that xk is a sampled and a scaled version of DTFT, that is x a omega, okay. So effectively we have to draw discrete samples from the DTFT that basically gives us, and then scale it by 1 by n to get the DFS. Now we are going to look at what is called as discrete Fourier transform. Abbreviated as DFT, okay. So let us say we have an aperiodic discrete signal which we have represented by XAN. So, let us say we are interested to find its frequency domain representation. Okay. And we just discussed that the frequency domain representation of this signal can be found by finding DTFT of this signal. However, the DTFT we would get, that would be a continuous spectrum, okay, and for practical purposes we would like to work with a discrete spectrum, okay, and therefore we are going to see an alternative approach to represent the frequency domain characteristics of this signal, okay. So, we are going to look at an alternative approach to find the frequency domain representation of XAN. Therefore, what we do is that we construct corresponding periodic signal, okay, that is Xn, okay, by repeating the copies of Xan, okay. So, that is the periodic signal, and then we find the discrete Fourier series of this, okay. We can find its discrete Fourier series, and the discrete Fourier series we know that it is basically periodic, and one period of discrete Fourier series can be used to represent the Xn in the frequency domain. So, one period of DFS describes Xn in the frequency domain. Therefore, one period of DFS is referred as discrete Fourier transform, DFT. So, and let us represent this DFT by symbol xk over bar, right. Xk is the DFS and x bar k is the DFT, and therefore we write DFT in this manner, that we say that x bar k is equal to xk for k varying from 0 to n minus 1, right, and it is equal to 0 otherwise. For other values of k it is 0, and it is only it is equal to xk, the DFS, for k varying from 0 to n minus 1. And now if you substitute xk here, then that would be nothing but 1 by n x n e to the power minus I k 2 pi upon n small n, with n varying from 0 to n minus 1, and here this is true for k varying from 0 to n minus 1 and 0 otherwise, okay. So, here we can also replace xn by xan, because the summation is only for range 0 to n minus 1, and therefore xan also describes the signal in that range. So, therefore, we can also write this expression as x bar k is equal to 1 by n is equal to 0 to n minus 1 x a n e to the power minus I k 2 pi by n, and this is equal to 0 otherwise. This of course is true for n minus 1 to 0. So, this is nothing but the expression for DFT. This is nothing but DFT. So, it means that if a periodic signal XAN is given, then we can implement this equation to find the DFT of the signal. And now we should note that here the DFT is now discrete, it is not continuous, it is discrete and it is finite, correct. So, while the DTFT was continuous and the DFS was periodic, okay, extending from minus infinity to plus infinity. Okay, so but the DFT is not only discrete but it is also finite. We can also now similarly define inverse DFT. Inverse discrete Fourier transform. That is, if the DFT of the signal is available, then how can we reconstruct the discrete signal again? That is something which can be done by inverse DFT, and therefore this basically we can write as x a n summation from x bar k, which is the DFT, e to the power I k 2 pi by n with k varying from 0 to n minus 1, and this is valid for samples n is equal to 0 to n minus 1, right, and it is 0 otherwise. Okay. So this is nothing but the inverse DFT. So another point should be noted here that the range of k we have defined from 0 to n minus 1, but we can also define the range of k from minus n by 2, okay, to going from 0 up to n by 2 minus 1. So either of these ranges can be used, the index k, it can be from minus n by 2 to n by 2 plus minus 1 or 0 to n minus 1. So we also note that in the expressions we got, the factor 1 by n appears in the expression for DFT, but in literature alternative derivations of these expressions exist, and there the factor 1 by n appears in the expression for IDFT. So let us now summarize the results we got. Okay. So we first studied DFS. So DFS is discrete and periodic. Okay. Then we studied DTFT. Now DTFT is continuous and periodic. Okay, so DFS spectrum is discrete and periodic, DTFT spectrum is continuous and periodic, and DFT is discrete and finite, that is aperiodic. Okay, and we should note that the XAN is also discrete and finite. So now in practice, which of these tools should be used for finding the frequency domain representation, DFS, DTFT or DFT? Okay, so which one to use? That is DFS, DTFT or DFT. So in practice the signal can be periodic or aperiodic. The signal we are measuring, it could be a periodic signal or aperiodic signal. So what we do is that we simply take the DFT of the signal that we have recorded. So if we have recorded a signal over time length t, then we just take the DFT of that. Okay, so we just take DFT of the recorded signal, which basically amounts to treating the signal as a periodic signal, okay, and finding its DFS and using one period of the DFS. That what it amounts to. So if now the actual signal is periodic, if the actual signal is periodic, then the DFT in this case would correspond to one period of the DFS of the recorded signal. So the DFT would correspond to one period of DFS of the recorded signal. But if the actual signal is aperiodic, right, then in that case the DFT we obtain, okay, would basically correspond to one period, okay, of the sampled version of the DTFT of the recorded signal. Okay, so DFT would correspond to sampled and scaled version of one period of DTFT of the recorded signal. Let us now look at what is mean by single sided spectrum. The DFT is basically defined over complex frequency axis. Okay, so DFT is defined over complex frequency axis, right, which means it has positive and negative frequency components. Okay, it has positive as well as negative frequency components, and since the measured signal is real, we have seen that for a real signal the DFT positive and negative frequency components, they are related by complex conjugate property. Okay, so the negative frequency components are complex conjugate of the positive frequency components, correct, since the signal is real, the negative frequency components are complex conjugate of positive frequency components, and therefore it should be possible to define the frequency domain representation using only positive frequencies. Okay, therefore frequency domain representation can be done only with positive frequencies. Okay, and such a spectrum or representation is called single sided spectrum. While the DFT, because it is defined over positive and negative frequencies, the spectrum has to be a two sided representation. Okay, so DFT is a two sided spectrum. So how this representation can be obtained? Let us go to next page. So let us say single sided spectrum is represented by say y bar k, right. So now we can say that the y bar k is the magnitude of y bar k is equal to that is the two sided DFT. Okay, and the phase of the y bar k is equal to minus tan inverse imaginary part of x bar k divided by the real part of x bar k. So that is the phase, and this is valid for k from 1 to up to. Okay. Now for k is equal to 0, the single sided spectrum DC component is equal to that of the DFT, right. And for n by 2, the component at n by 2, y bar n by 2, it is minus of x bar n by 2. Okay. So, using these expressions, therefore, it is possible for us to convert the two-sided DFT, okay, into a single-sided DFT or single-sided spectrum. Now, let us take a simple example. In fact, the example we considered in the previous lecture to see that how do these single-sided and two-sided DFT look like. Okay. So, we had taken the continuous signal as 20 cos 2 pi 2t plus 14 cos 6 2 pi 60. So, let us say the signal we are measuring is being described by this equation. Now, if we obtain the DFT of this, okay, using the sampling frequency of, let us say signal was sampled at 20 hertz and 1 second record of the signal was measured. So, the DFT here would be, so here we are representing the magnitude of the two-sided DFT, right, as a function of say frequency f in hertz. And now, so this spectrum now would be defined over minus 10 to plus 10, that is this is the 10 hertz, then we have this is minus 10 hertz, and then we are going to see now the positive and negative frequencies. So, we will have a frequency component at 2 hertz like this and also at minus 2 hertz of the same magnitude 10, right, and then we will have a component at 6 hertz, right, that is somewhere here, and also at minus 6 hertz, right, and the strength of this would be 7. So, this is nothing but the two-sided DFT, okay. This we can call as two-sided spectrum. We can also call it as complex DFT or two-sided DFT. Now, if we determine the single-sided spectrum, then that can be plotted in this manner. It would look something like this. So, here we are showing the magnitude of the single-sided spectrum as a function of frequency, okay. And now this would be from 0 to 10 hertz, okay, and then we will have a component at 2 hertz like this, and its amplitude would be 20, and a component at 6 hertz like this with amplitude 14. So, this is a single sided spectrum. Okay. So, let us now look at how the time domain parameters of the discrete signal are related to the frequency domain parameters of the DFT. Okay. So, relationship between time and frequency domain parameters. So, most of these relationships we already have used in the this and the previous lecture, but let us review them, to have a clear view of those relationships. So, the first parameter is time resolution, which is the time gap or time interval delta t, and this is actually equal to 1 by Fs, right, where Fs is the sampling frequency. In hertz. Okay. Then we have the frequency resolution of the DFT, and that if we represent by delta f, then this would be equal to 1 upon t, okay, where t is the record length of the recorded signal. Then we also have the number of samples in t, that we represent by capital N, and this is equal to t upon delta t, okay. Other parameter is that what is the highest frequency component in the spectrum, okay, and the highest frequency component in the spectrum basically defines the frequency range of measurement, right. So, if we represent it by say f max, that is the highest frequency component in DFT, and this should be equal to n by 2 into delta f, because delta f is the frequency resolution, and we can determine n by 2 number of real frequency components. So, the complex frequency components or positive and negative frequency components, they exist from minus n by 2 to n by 2 minus 1, right, and if we convert it to single sided spectrum, then actually we get only 0 to n by 2 number of frequency components, okay, because every positive and corresponding negative frequency component together make up a real frequency component, okay. So, therefore, we have n by 2 into delta f is the frequency of the highest frequency component in the DFT. So, therefore, we can write in place of n, we can write t upon delta t, okay, and t into delta f is nothing but 1. So, we get 1 upon 2 delta t, and 1 upon delta t is nothing but fs. So, we get fs by 2. So, it means that the highest frequency component we get is actually equal to fs by 2. So, you can see in this way we have 4 relationships, 1, 2, 3 and 4, okay. So, we have 4 equations which relate the time and frequency domain parameters, and we have how many variables? Variables or parameters are delta t, then we have delta f, then we have record length t, then we have number of samples n, then we have sampling frequency, and then we have the highest frequency in the spectrum, right, which basically defines the frequency range of the spectrum. So, there are 6 variables, right, 6 parameters. So, it means that 2 of the parameters, okay, 2 parameters can be chosen freely. So, we can 2 parameters can be chosen freely. So, once these any 2 parameters are chosen, the other 4 parameters get automatically fixed from these 4 relationships. So, typically in practice we may like to choose say the record length. We may say that okay, we want to record the signal of this much duration, like 1 second, 2 second, 8 seconds, 16 seconds and so on, and then the other parameter could be f max, the frequency range of measurement, right. So, we may take from let us say 0 to 400 hertz or 0 to 1000 hertz or 2 kilohertz and so on. So, once these 2 parameters are taken, now the rest of the 4 parameters can be determined and they get fixed. They cannot be any more chosen independently. So, of course, if we want to let us say improve the frequency resolution, then we can understand from these relationships that can be done by increasing the record length t, right. Similarly, if I want to increase the frequency range of measurement, then from the relationships I understand that I need to increase the sampling frequency, okay, fs, then I can increase the frequency range of measurement. So, that is why these relationships are important, because they help us to basically determine that how different parameters can be chosen to suit our measurement. Now we are going to talk about what is called as fast Fourier transform, okay, abbreviated as FFT. So we see that evaluation of the DFT is computationally expensive. Evaluation of DFT is computationally expensive, okay. So the computational efficiency depends upon how many arithmetics and how many multiplications they need to be carried out in order to evaluate, right, DFT, and therefore higher this number, poor would be the computational efficiency. So FFT is basically a class of algorithms, okay, which basically efficiently compute the DFT. So what is FFT? FFT basically represents the class of a class of algorithms to compute DFT efficiently, okay. And the FFT algorithms basically make use of the symmetricity and periodicity of the structure of DFT, okay, and thereby devise algorithms which can reduce the amount of computation. So they make use of they exploit the symmetry, and periodicity in DFT, okay, to reduce the computations, the number of computations. So one of such algorithms was first proposed by Cooley and Tukey in 1965, okay. So it is seen that if the DFT is computed without any FFT algorithm, it is a direct computation is done, then the direct computation of DFT is proportional to n square, where n is the number of samples. In the signal, that is xn, and generally it is preferred that n is equal to power of 2, right. So 2 to the power 8, 2 to the power 10 and so on. So and then with FFT the computation of DFT is proportional to n log 2n, okay, and therefore n log 2n is substantially less than n square, and that is why the FFT algorithms are computationally efficient. So that is why the modern signal analyzers mostly use FFT algorithms to compute the DFT, and that is also help to basically compute the DFT in real time. So in this way, today we looked at the frequency domain representation of discrete aperiodic signals. And in the process we developed the concepts of DTFT and DFT, and we also briefly studied what is FFT. We can now stop here, we will continue in the next class. Thank you.